Hello, let's remind ourselves of the translation from polar coordinates to rectangular coordinates. Rectangular coordinates are the ones we're most familiar with x and y values. If you happen to know r and theta, then you can use these two equations, to translate into x and y values. If you know your x and y values, then you can use these two equations to translate into polar coordinates to give you r and theta. Let's look at an example of how to write a region in polar coordinates. The radius or distance from the center is 2 units, and we're going to close in this little quarter circle. This region has a radius that expands from 0 out to 2. And so we can write 0 less than or equal to r less than or equal to 2. The angle rotated from what you would think of as the positive x-axis is pi over 2. So your angle is swept from 0 to pi over 2. Another region in polar coordinates, you would have a radius, and this is an annular shape. This part is like a donut hole. From 1 to 3, we count that radius. R is between 1 and 3 units. And we go a full circle here, so theta is 0 to 2 pi. These are examples of polar sectors, and that's where you have a region in polar coordinates where r is trapped between two different radii values, and your angle theta is trapped between two angular values. In polar coordinates, your r will be trapped between two functions of theta, and theta will be two fixed angles, and those will be the bounds for your region. Theorem: let R be a plane region consisting of all points x, y equal to r cosine theta, r sine theta, satisfying the conditions where all of it is greater than or equal to 0, but your r is specifically trapped between two functions of theta, and your angle is between alpha and beta, two fixed values. The difference between alpha and beta is going to be somewhere between 0 and 2 pi. If g1 and g2 are continuous on an interval alpha beta, and f is continuous on r, then you can write your double integral as the integral from alpha to beta with your d theta on the ends, and those represent your theta parameters values, and dr is your lower and upper first, second function of theta. So we're going to put in our function in polar coordinates times r. This r is real easy to forget, and I'll remind you to hang on to it. And then we looked at past videos of how to solve double integrals. An example of what's called R simple is a region where you have a polar sector cut off by a lower and upper function of theta. The first angle is alpha, the ending angle is beta, and then you've got some thickness or strip representative of theta, delta theta. You can also have a theta simple, and that's where your theta is variable but your r is fixed. H sub 1 of r, H sub 2 of r, and then you look at this strip where it's delta r, where the radius changes. Theta changes based on the angle swept out. Let's move to an example. Let R be the annular region lying between the two circles x squared plus y squared equals 1 and x squared plus y squared equals 5. Now recall, the equation of a circle is x squared plus y squared equals radius squared. So 1, its square root is also 1. And that's where we get that value. That's our inner circle. In the second equation, the radius is square root of 5. And that represents the radius of the outer circle. The radius that we're looking at is between 1 and square root of 5, causing us to have this region. This is our capital R. We're going to evaluate x squared plus y using the differential D area being the area of this. And it looks like a donut. It looks like a flat donut. Our region R is between 1 and square root of 5, and that's what we looked at over here. Because that makes a full loop, our theta is between 0 and 2 pi inclusive. So we're going to calculate this double integral on the next page. The polar boundaries, and I wrote these down as a reminder, R is between 1 and square root of 5, theta is between 0 and 2 pi. X squared is R squared cosine squared theta, and y is R sine theta. And that's from the first page in our conversions. Therefore, we can write our function x squared plus y as R squared cosine squared theta plus y, which is R sine theta. And this is that R I mentioned earlier about not forgetting. Once you put in your function in polar coordinates, you're also going to have an R that multiplies with it, and then dr d theta. Theta runs from 0 to 2 pi. R runs from 1 to square root of 5. Now the integral looks intimidating. I'm going to go ahead and distribute this R, and that's going to give us R cubed cosine squared theta plus R squared sine theta. Remember to work inside out, so we're going to take the antiderivative with respect to R. That's R to the 4th over 4. The theta terms are constant, so they don't change. Second term, R3 over 3. Sine theta stays the same, and we'll evaluate at our upper and lower radii limits. Substituting in square root of 5, plug them right in for R, minus, and then substitute 1 in for R, just sub them right in, only for R. Very tedious calculations here. This is square root of 5 to the 4th, which is 5 squared squared. That's 25 fourths. Cosine squared theta. I'm just translating this. Square root of 5 to the 3rd is 5 to the 3/2 power. I didn't actually simplify here. Distribute minus 1/4 cosine squared theta. That's just a 1. And then minus 1/3, stays 1/3 sine theta, d theta. Simplifying, 25 fourths minus 1/4, that's 24 fourths, which is 6 of the cosine squared terms. And then this is where you got to watch it. 5 to the 3/2 is 5 square root of 5, because that's 1.5. So you have 5 square root of 5 thirds. Over here you have a 1/3. So that gives you 5 square root of 5 minus 1/3. That's very tedious right there. Now we can take the antiderivative with respect to theta. This, using a power reduction formula, is how I get this underlined in red. If you multiply by 6 here and here, that 2 cuts into 6 3 times. And when you distribute 3, that's where those 3's come from. I didn't change anything in the back. Now let's take the antiderivative. That's 3 theta. 3/2 sine 2 theta. If you don't believe it, take the derivative. That's cosine 2 theta times 2 which will cancel that one, leaving only the 3. And then here, I made a small error. I got to fix it. This should be cosine. There we go. The antiderivative of sine is negative cosine theta. The coefficient didn't change. And now, when we sub in our values, okay, when you sub in a 2 pi and a 0 into this term, sine of 4 pi and sine of 0 are 0. So this block in the middle goes out by default. 2 pi and 0 subbed in make this equal to 1. So the first time through, you're going to get a negative this numerical value. And then back here, if I had written this out, you would get a minus another negative 5 squared root of 5 minus 1 over 3, which would make it positive. So it turns out that due to sign changes, this block, and if I'd written it out with a 0, would cancel out back here, leaving only 3 theta times 2 pi. So 3 times 2 pi is 6 pi. 3 times 0 is 0. So that is our area. Use polar coordinates to find the volume of the solid region bounded above by the hemisphere. Z equals square root of 16 minus x squared minus y squared. And below by x squared plus y squared less than or equal to 4. Now that's a circle centered at the origin with a radius of 2, but because of the inequalities less than or equal to, that is this entire region on the border and inside. So it's a filled-in circle. Our region is bounded by the filled-in circle centered at the origin with radius 2, because 4 is 2 squared. Remember, x squared plus y squared is equal to r squared. So that tells us that our radius is between 0 and 2. Remember this. And because this filled in circle makes a full rotation, our theta is trapped between 0 and 2 pi inclusive. Also note that our hemisphere can be rewritten as 16 minus x squared plus y squared, making that an r squared. Square root of 16 minus r squared. Now we're ready to integrate. Theta goes from 0 to 2 pi. R goes from 0 to 2. This is our function in polar form. Don't forget the times r. That little bitty r is hard to remember. I move it out front. We could integrate this by adding 1 to the power and dividing by result if the derivative of this is present. All we need to do is make sure there's a negative 2. If we put in a negative 2, we have to take it back out and balance it out here. So times negative 2 divided by negative 2. Now, and it's sort of like U substitution, but I'm not going to go through the trouble of writing it out. It's this term, because its derivative is present, it's this term, add 1, that gives you 3 halves, divide by the result is 2/3. Dividing by 3 halves is the same as multiplying by 2/3. 2/3 times negative half is a negative 1/3. 16 minus 2 squared to the 3 halves minus 16 minus 0 squared to the 3 halves. And it's just a long problem. I ran out of real estate. I tried to space it so it'd be easier to read for you guys. Continued on the next page. Negative 1/3, integrating from 0 to 2 pi. These are those values simplified. 16 to the 3/2, square root of 16 is 4, cubed is 64, and then this one was really gnarly. 16 minus 4 is 12 to the 3/2. I calculated that over here. That's the square root of 12 cubed. Since 12 is 4 times 3, that's 2 square root of 3. Cubed is 8 times 3 square root of 3, because it takes 2 of them to get a 3, but then there's still one more radical 3. Anyway, check with your calculator. 12 to the 3/2 has the same value as 24 square root of 3, and that's where I made this jump from here to here. It's over here in red. Now, integrate with respect to theta. This is a constant, so you just throw your little theta on here, evaluate at 2 pi and 0. This number times 2 pi. This number times 0, which will be 0. So you only have to make this calculation with the 2 pi. Distribute through, rearrange your terms, and it's approximately equal to 47, but this is either this one or that one is fine. Let's look at another example. Find the area enclosed by r equals 3 cosine 3 theta. Check your email for a link on YouTube to generating the graph of these using your TI-84. It's a real quick 3-minute video. The person explaining it does a great job, easy to follow along, and it will allow you to type in an equation that's in polar form instead of rectangular, and your calculator will generate this petal type graph. We're going to let r be one petal of the graph, and I highlighted this one over here. Theta will run from negative pi over 6 to positive pi over 6. And r will be anywhere from 0 to 3 cosine 3 theta. 0 here, all the way out to 3 cosine theta. Do not forget that little bitty r is in here. And since we've accounted for the function up here, we don't have to write it in here. The antiderivative with respect to r is r squared over 2, evaluated at 3 cosine 3 theta and 0. That is going to be 9 cosine squared 3 theta over 2 minus 0 squared over 2, which is 0. I didn't write anything here. I'm going to move 9/2 out to the front. Any constant or scalar you can move out in an integral, whether it's single or double, you can move it out to the front. I'm going to use a power reducing formula. From here to here, I use this formula. Think of this as 3 theta, then this will be 2 times 3 theta, 6 theta. This 1/2 I pulled out front, and that's why that changed to a 9/4, was because I pulled that 2 out from the denominator. 1 plus cosine 6 theta, taking the antiderivative with respect to theta, is theta minus 1/6 sine 6 theta. If you don't trust yourself, take the derivative. That would be cosine 6 theta times 6, which would eliminate the 1/6. Evaluating at pi over 6 and then at negative pi over 6, make substitutions. Pi over 6 plus pi over 6 is 2 pi over 6. Those 6's cancel. Sine of pi is 0. Sine of pi is 0. That's why I drew little arrows to 0 out those big blocks. 9/4 times 2 pi over 6 is 18 pi over 24, which reduces to 3/4 pi. Don't forget, this was only one of 3 petals, and that's why I put 1/3 a. To get the full area, you multiply your answer by 3. If this graph had 4 petals, then you would use a 4 times your area from here. And in our last example, we're going to look at a theta simple region. Find the area of the region bounded above by the spiral r equals pi over 3 theta, and that's this little spiral here. You can use your graphing calculator along with the help of that YouTube video to see these graphs, by the way. And I encourage you to use that on your homework, because some of your homework will ask you to find the region and then find the area. R is fixed between 1 and 2, so I'm going to put radius out here on the ends. Normally it's been dr d theta, but this is backwards. Dr on the outside from 1 to 2, theta on the inside, and that's from pi over 6 to pi over 3. Oh, let me take that back. Let's go back to our spiral. If you solve your spiral for theta, pi over r is equal to 3 theta, so pi over 3r is equal to theta. That's what I meant to say. Theta's on the inside. I got a little confused. 0 to pi over 3r. And again, I solved this one for theta, and that gave me the upper limit. Taking the antiderivative with respect to theta is r theta. Plug in pi over 3r for theta, minus plug in 0 for theta. Well, that's going to go to 0. These r's cancel, leaving pi over 3. And then the antiderivative with respect to r is pi over 3r, evaluated from 1 to 2. That's going to be 2 pi over 3 minus 1 pi over 3, which is pi over 3. I hope this video helps. I apologize for a few hiccups I made. This stuff in my mind is confusing. I know it's got to be rough for y'all. Just hang in there and study as hard as you can, and reach out by email or phone or swing by the office if anything gives you a lot of fits.